Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Welcome to Electronics. I am Madam Rosmina Zuin Abdul Rahim. To get the blessing from Allah, let's have a look on this hadith. Abu Hurairah radhiyallahu anhu reported the Messenger of Allah sallallahu alaihi wasallam said, "Is not the world cursed and everything in it, except for the remembrance of Allah and what facilitates it, the scholar or the student?" Source Sunan At-Tirmizi. Our Prophet sallallahu alaihi wasallam said that the world is being cursed actually by Allah. What does it mean? It means that this world tends to bring us away from Him. We tend to be attracted too much to the world until we forget why are we here today in this world. Okay, so what can save us from this cursed world actually by always remember Allah. So we can remember Allah through our prayers, through reading Quran, through all the good things that we do in our lives that can always make us to remember Him. And what facilitates it? For example, being the student of knowledge, we tend to practice all the beneficial knowledge. Obviously, this knowledge will bring us closer to Him as well, will be part of those who remember Allah. And by doing so, hopefully, it can save us from this cursed world. We are now on chapter 7, FET Amplifier. This video is actually related to chapter 7a, which has two subtopics. The first one is on basic FET amplifiers. The second one is on the common source amplifier, where it has three types: the source grounded, the one with the RS, and the one with the bypass capacitor. For the first subtopic on basic FET amplifiers, we should take note that for a linear amplifier function, FET is normally biased in saturation region. When we come across DC analysis before, we know that FET normally will be operating under two regions actually, right? The non-saturation region and saturation region. So in order for us to make that FET circuit to be a good linear amplifier, we need to make it to be biased under saturation region only. In order for us to do AC analysis of FET amplifier, first obviously we need to know how to represent FET in AC circuit. So basically FET, we know it has three terminals, right? The gate, drain and the source. So basically between the gate and the source, it is being represented with VGS. Okay, and as you can see here at the gate, it is represented with open circuit indicating the oxide layer, and between the drain and the source we have the current source GM-VGS, and in parallel to it we have small R0. And what will be the GM value for this? Actually is given by 2 cert Kn ID, and the small R0 actually is given by VA over ID, where VA is the early voltage and it is given by 1 over lambda. But as can be seen from here, all the AC parameters value actually are related to the ID value, where we need to do the DC analysis first to get the ID, then only we can find for the GM and R0. Then this slide actually shows you how to do the derivation of GM, where actually it started from this ID equation, where ID is equal to Kn times VGS minus VTN squared. We expand the equation, then we get the differentiation of ID with respect to VGS. Okay, then later it will give us in this form, and GM is actually equals to 2 Kn cert ID over Kn. Okay, so if you rearrange it, in the end we are supposed to get GM equals 2 times cert Kn ID. For the derivation of R0, the small R0, we can refer to these steps, but at the end of the day we can say R0 is actually given by VA over ID. What is VA? VA is the early voltage, always will be given. Now we come to the second subtopic, which is on common source amplifier. So when you come across common source, you should take note that actually it's just similar to the common emitter when we are considering BJT amplifier, where the output is measured at the drain terminal for this common source, and the gain should always be negative. And for this particular common source, there are three types that we need to consider. The first one when the source is grounded, the second one with the source resistor RS, the third one with bypass capacitor CS. These three types actually similar to the common emitter amplifier, where it has all the three types that we discussed before. Now we come to type 1, common source with the source grounded. So as you can see from this FET circuit where we have the drain, gate and the source. So as you can see here, the source is grounded, and you know this is the common source amplifier because as you can see here, output voltage V0 is measured at the drain terminal. Okay, so this is type number 1. So similar to common emitter amplifier, the first thing first when we are considering for AC analysis, obviously we need to draw the small signal equivalent circuit where we always start with the FET model, the transistor model, right? Okay, so for NMOS here, the FET model is represented with the one that I marked in the box here, where between the gate and the source we have VGS, and we also have an open circuit at the gate indicating the oxide layer, remember? And between the drain to the source we have GM-VGS, and in parallel to it we have R0. Once we are done with the FET model, then only we can draw the remaining of the components. For example, as you can see here, the source is grounded. So in this case, the source is directly grounded. And at the gate, we have R1 and R2, and apparently R1 is connected to VDD, which is actually grounded in AC. Remember, DC voltage is grounded. So we can say R1 and R2, they are actually in parallel. And similar to BJT amplifier before this, the same goes to capacitor when we are considering AC analysis, where capacitor should be replaced with short circuit. Okay, replaced with short circuit. So that's why at the gate here it is now connected directly to RSI and obviously connected to the VS, the source. And we have a look at the drain. We have RD between the drain and the ground. So that's why here we have RD between drain and the ground. So this is the small signal equivalent circuit. So to understand better about common source amplifier, let's have a look on this one example where all the transistor parameters are given, VTN given, Kn value is also given, and lambda is also given equals to 0. And in this case, obviously, we need to do the DC analysis first, remember? Because we want to find for ID, then only we can find for all the small signal parameters. So that's why in this case, if we are considering DC, obviously this capacitor should be open circuit, meaning we are having similar to voltage divider biasing circuit where we need to do the Thevenin equivalent. So in this case, if you solve for this, you are supposed to get RTH is this value and VTH is this value for this particular example. Then for the DC analysis, it's similar to the one that we discussed before where we have all the 5 steps for us to do. First, we identify for VGS value, remember, where in this case VGS is actually equals to VTH, the Thevenin voltage, straight away equals to 1.905 volt. Then for the second step, we assume it's in we assume it's under saturation region. So that's why we use this ID equation where we substitute all the values, leaving our ID equals to 0.244 milliampere. For the third step, we do KVL at the DS loop. So from the KVL equation, we are getting IDRT plus VDS minus VDD equals to 0. Then from there, we are getting VDS equals 2.56 volt. And step number 4, we need to find for VDS saturation. In this case, is equal to 1.105 volt. Then we check in step number 5 whether our assumption is correct or not. Obviously, 2.56 is larger than 1.105, meaning our assumption is correct. From there, we can proceed. Then we can calculate for GM value, which is equal to 2 cert Kn ID. Then obviously in this case we can get the GM value. How about R0? R0 is infinity because in this example lambda is 0. So before we proceed to the AC analysis of common source amplifier. As I mentioned just now, it's very similar to common emitter amplifier. As you still can recall, in common emitter amplifier, we start by finding for R0 value, then get the V0 equations, then we get the Ri, later we get VBE in terms of Vi. So if you check the steps here for the common source, okay, actually it's quite similar. We start by looking for R0, then get the V0 equation, and in this case we get VGS in terms of Vi. We get VGS in terms of Vi. We don't have to find for Ri because automatically in this case Ri is actually equals to RTH. In the case that you need to consider R0, the small R0, if let's say we are considering another example, obviously for the step number 1, you have to consider small R0, and later your V0 equation, obviously it will be modified a bit because R0 now will be small R0 in parallel to RD. But what I'm trying to say is the rest just will be the same, where step number 3 we get VGS in terms of Vi. Okay, straightforward. And then substitute accordingly, because remember we want to get the voltage amplifier model where we want to find for the open circuit voltage gain. So that's why we have AVVI equals to V0, where we already have V0 in terms of this negative GM VGS times R0 in parallel to RD as in step number 2. Then from there we know that VGS is actually equals to Vi, so straight away we substitute, then we can cancel it out, leaving our AV open circuit voltage gain equals to negative GM times R0 in parallel to RD. Okay, now coming back to our example just now, you make sure you know how to draw the small signal equivalent circuit. As I always mention, you start by drawing the FET model. Okay, so in this case we have between gate and the source we have VGS, and at the gate we have open circuit like this, and between the drain and the source we have GM VGS, and here we don't consider small R0 because R0 is infinity. But other components we just draw the same, where we have RTH, we have RSI and connected to VS, and later if you double check with the circuit just now, at the drain we have RD connected between the drain and the source. Okay, once you are done this small signal equivalent circuit, you are ready for the AC analysis. Step number 1, get R0. In this case, it's very straightforward. R0 equals to RT. Then step number 2, we get the output voltage where V equals to IR, remember? So V0 equals to negative GM VGS equals to the current, and R is the R0, which is actually RD. So you just substitute whatever values that you already know, leaving your V0 in terms of VGS, V0 in terms of VGS, because other values that we already know we straight away substitute. Then later step number 3, we get VI in terms of VGS. So as can be seen from here, VGS is between the voltage between the gate and the source, right? So the same goes to VI, where VI is actually in parallel to it, meaning we can say VGS is actually equals to VI. Then if we go further to consider for voltage amplifier model, remember we have AVVI equals to V0 because we want to consider for open circuit voltage gain, and V0 before this we already have in terms of VGS, remember we have negative 4.42 VGS. Okay, substitute accordingly, and VGS is actually just equal to VI, so we can cancel it out altogether, leaving our AV, the open circuit voltage gain, equals to negative 4.42. Then once we have the AV, the open circuit voltage gain just now, we can represent our common source amplifier here with all the values, where we already have the Ri, we have the R0, and we have this AV already. Then we are considering the source, okay, connected to our amplifier, where we have RSI and VS. So the next step will be to find the new voltage gain, obviously the V0 over VS. So in this case we need to relate VI in terms of VS. Obviously in this case we use voltage divider. So if you use voltage divider, you are supposed to get VI in terms of VS. In this case, 0.9975 VS. Then later, what do? Here we check at the output side. At the output side, there is no load resistor. So that's why in this case, we can straight away see V0 equals to AVVI. Then AV we already found just now. And VI we already have in terms of VS. So we substitute accordingly. Later, we are getting the voltage gain V0 over Vs, which is equals to negative 4.41. Is the voltage being amplified? Yes. How much? By 4.41, and obviously it is inverted in the opposite polarity. Now we come to the second type of common source, where now the source is no longer grounded, but instead we are having a source resistor Rs. So as can be seen from here, we have Rs, meaning the source is no longer grounded. But other things are just about the same, where in order for us to do the AC analysis, we have to do the DC analysis of it by finding for the ID. In order to do that, we need to find for the Thevenin equivalent circuit. Then later, remember all the 5 steps that we need to do for DC analysis. First, you need to find for VGS, right? So in this case, you need to do some kind of KVL at the GS loop. This is just kind of revision because we have discussed this before in previous topic. So now you are having VGS in terms of ID. Then later in step 2, you use the saturation region ID equation. Then substitute VGS in terms of ID, and at the end of the day, if you do some kind of rearrangement of this equation, you will have it in the form of quadratic, where if you solve for this, you are supposed to get 2 ID values, right? So in this case, ID is given as 0.589 and 0.189. You don't know which ID value should you use. Later, what you can do is go back to step number 1, substitute ID value, both ID values in this VGS equation. Then you are supposed to get VGS equals to 0.233 volt and VGS equals to 1.43 volt. The question is, which VGS value should you choose? Obviously, the one which is larger than the threshold voltage. Okay, so obviously, in this case, we should choose VGS equals to 1.43 volt. Why? Because it is bigger than the threshold voltage. Then later, step number 3, we do KVL at the DS loop. Okay, we get VDS value, we get VDS saturation, and check whether our assumption is correct or not. Then only we can use that ID equation to calculate for GM, in this case, all the small signal parameters. And for this particular example, lambda is also 0, meaning our R0 is infinity, where we don't have to consider in AC analysis. So before we go further with the AC analysis of common source with RS, actually let's recall this amplifier is similar to common emitter with RE, where in this AC analysis, remember all the steps, we start by finding for R0, then we get the V0 equation, then later in common emitter you are supposed to find for RIB, input resistance looking at the base, then only you can find for RI, then later you can relate VBE in terms of VI, right? Now let's have a look on common source with RS. Actually, it is much simpler here because step 1 you get the R0, okay, then later step 2 we get the V0. Then later, in this case, you just straight away relate VI in terms of VGS using KVL. So just now we discussed about get VGS in terms of VI in common source with RS where we do KVL. So this should be the KVL equation where VI is actually equals to VGS plus the voltage across RS where I is GM VGS. Okay, then the R it should be the RS. Okay, so from here what you can do is you can get the VI in terms of VGS. And later step number 4, to get the open circuit voltage gain, as usual AVVI equals to V0, and V0 we already have in terms of VGS in step number 2. Then substitute accordingly where we already have VGS in terms of VI from step number 3. Then later we can cancel it out, leaving our open circuit voltage gain in this form. So to understand better about common source with RS, let's straight away have a look on this particular example where we start by drawing the small signal equivalent circuit. As I always mention to you, always start with the FET model, then only you draw the remaining of the components. Okay, then later from this, once you are done with the small signal equivalent circuit, then only you can do the analysis, AC analysis of it. Step number 1, get R0. In this case, it's straight away equals to RD. Step number 2, get the output voltage where V0 equation equals to I0 R0. So that's why you substitute whatever values you know. Then later you are having V0 in terms of VGS. Then step number 3, you get VI in terms of VGS through KVL equation. So in this case, you are supposed to get VI equals to VGS times 1 plus 2.616, which later you can simplify in terms of VGS component. Okay, then later because remember just now we already have V0 in terms of VGS and we already have VI in terms of VGS as well. So what we can do here, actually we can relate AVVI to V0, remember? Then this V0 actually we already have in terms of VGS, and this VGS we represent it in the form of VI. Okay, so we have everything, we cancel it out, then we have the open circuit voltage gain equals negative 2.41. So once we know all the parameter values, for example, we have Ri, we already know the R0 as well as we know the open circuit voltage gain, we can represent it in the voltage amplifier model by considering all the source and the load if there is any load. And for this particular example, obviously the next step we need to have Vi in terms of Vs. But for this example, there is no resistor at the source, so obviously we can say Vs is actually just in parallel to Vi. So here that's why we can say Vi equals to Vs, meaning we don't have to do voltage divider. Later at the output side, we consider V0 equals AVVI because we don't have any load resistor connected to it. So AV we already know from the open circuit voltage gain, and in this case Vi equals to Vs. Obviously the voltage gain V0 over Vs equals to negative 2.41. Is the voltage being amplified? Yes. By how much? By 2.41. But obviously since we are having negative sign, we can say the amplified voltage actually is in inverted polarity. We are still talking about common source amplifier, but we are coming to type 3 where we have the bypass capacitor CS. Then always relate this common source amplifier to the common emitter, remember? Where in common emitter we also have type 3 where we have bypass capacitor CE. So the same thing goes to here where actually type 3 is similar to type 1 because we have the bypass capacitor, meaning although you are having any resistor in parallel to it, but actually it won't be considered because you are having a capacitor in parallel to RS. As for the AC analysis, let's compare the common emitter with CE to the one common source with CS actually is quite similar, where for common emitter with CE, we start with the R0, then get the V0 equation, we get RI, later we get VBE in terms of VI. And obviously, because remember we are talking about type 1 actually, which is similar to type 3. So coming to common source with CS, we do the same, where we get the R0, we get the V0 equation. It's just that for this case, we don't need to consider any resistor. Straight away, we consider VGS in terms of VI. So for the AC analysis of common source with CS, we already discussed step number 1, 2, 3 just now. Then later you just continue with AVVI equals to V0, where V0 we already have in terms of VGS. Then we already have also in step number 3 where VGS equals to VI, so we substitute accordingly, so that from there we can cancel it out, leaving our open circuit voltage gain equals to negative GM times R0 in parallel to RD. Okay, let's have a look for this particular example where we are considering type number 3. How do we know? Because we have a bypass capacitor CS here. Okay, in parallel to CS, we have a current source. Current source IQ actually indicates the drain current here equals to 0.5 milliampere, meaning we don't have to do the DC analysis of it because we already know the drain current value. Then from there, we know R0 is given as infinity. Okay, then GM, you get it from the formula. Then you have GM value equals to 1.414 milliampere per volt. Then before you proceed to the AC analysis, try to draw the small signal equivalent circuit. As I mentioned to you, always start with the FET model. Remember, where we have the VGS between gate and the source, where we have open circuit here, and we have the current source here, GM VGS from the drain to the source, and we don't consider small R0 because R0 is infinity. After you are done with the model, then only you draw the remaining of the component. For example, at the gate here you have RG, yes, you have RG, and at the gate later you have capacitor, but always replace with short circuit in AC analysis, so that's why G is directly connected to VS. And at the drain, as you can see here, we have RD between the drain and the DC voltage, and obviously DC voltage is replaced with a ground, so that's why RD here is between the drain and the ground. And obviously in this case, since we are having bypass capacitor at the source, we can say actually the source is grounded because the capacitor is replaced with short circuit, so that's why it is as if the source is connected directly to the ground, although in parallel we are having a current source here, meaning we don't have to consider it in AC analysis. So as we know, type 3 just similar to type 1, right? So we start with step number 1, finding for R0 and get the V0 equation in terms of VGS, and from here very straightforward, VGS equals to VI. Okay, then obviously later you get the open circuit voltage gain because we already have V0 in terms of VGS and VI equals to VGS. So we relate AVVI to V0, where V0 in this form and VGS we know equals to VI. Substitute accordingly. From there we can get open circuit voltage gain. Then for this particular example, we need to find the new voltage gain where V0 over Vs. Then obviously in this case we need to relate Vi in terms of Vs, but for this particular example you know that Vi is actually in parallel to Vs, where we say Vi equals to Vs. We don't have to do voltage divider, and at the output side we can straight away say V0 equals to AVVI because there is no load resistor. So AV is already obtained just now, open circuit voltage gain. Vi is equals to Vs, so straight away substitute, then we can get the ratio of V0 over Vs, which is our voltage gain that we are looking for, which in this case equals to negative 9.898. Is the voltage being amplified? Yes. By how much? By 9.898, and obviously it is in inverted voltage. So as a summary, when we are considering all the three types, okay, first we can get the open circuit voltage gain in this form, okay. Then we can consider for Ri, if it is asked for us to find for it, straight away we know Ri is actually equals to Rth, and R0 basically depends on the example. It might be equal straight away equal to Rd, or when we are considering small R0, so your R0 will be equals to R0, small R0 in parallel to Rd. It all depends on the questions. So I think that's all for today. Let's recall a bit. We already covered basic FET amplifiers, okay, where we consider the small signal parameters GM and R0. Then we discuss all the three examples related to common source. So take note, it's very similar to common emitter amplifier that we discussed in BGAT, where we have all the three types. And I think for FET it is much more simpler, and it's more straightforward. So I think that's all related to the video. Thank you for staying until the end of the video. May Allah bless whatever knowledge you gain. May Allah protect you from any harm and guide your heart always in whatever you are doing. So that's all for today. Bye.